Welcome to the Math Record. Today we'll learn about the Fundamental Theorem of Algebra and other theorems. This video will be the fourth part in Chapter 2 of our Precalculus class. In this class, we'll be learning Descartes' rules of sign, rational zeros theorem, bounds on zeros, intermediate value theorem, conjugate pairs theorem, and the Fundamental Theorem of Algebra. All of these theorems will help you find the zeros of a polynomial. In this video, I'll be interchanging between zeros and roots, but they're basically the same thing. Let's focus first on the fundamental theorem of algebra. This theorem is very simple. It basically states that any polynomial of degree 1 or higher has at least one root. So if it's degree 1 or plus, then it has at least one root, one complex root. So it could be imaginary. So if it's like x plus 1, there's going to be one root, which is negative 1. If it's x squared plus 1, that means there's also one complex root, which is just basically I and negative I, right? So the fundamental theorem of algebra doesn't really do any math processes for you, but it tells you there are roots if you see like a linear or a higher polynomial. So that's the fundamental theorem of algebra. The next theorem that I'm talking about is really useful, and Precalculus will use this often to find zeros. It's called the rational zeros theorem. The rational zeros theorem states that the rational zeros of a polynomial is calculated by the factors of the constant divided by the factors of the coefficient of the largest power. So what does that mean? Okay, let me give you an example. We have f of x, right? And let's say that is 2x cubed plus x squared minus 7x minus 6. So what the rational zeros theorem tells us, the rational zeros theorem, sorry, right here, theorem tells us is that if we had to look for the factors of negative 6 divided by the factors of 2, because the factors of this divided by the factors of this all the time, the last term by the first term. So what it so the factors of negative 6, it has to be positive and negative. So the factors of negative 6 are plus and minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. All over, the factors are 2 of plus or minus 1 and plus or minus 2. So you have to find all the possibilities. So 1 divided by 1 is 1, 2 divided by 1 is 2, that's 3, and that's 4. So you have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, and plus or minus 5. And then you have 1 divided by 2, which is 1/2, so it's plus or minus 1/2. 2 divided by 2 is already 1, so which we already got. 3 divided by 2 is 3 over 2. And 6 divided by 2 is 3. So I already got it. These are all the possibilities. So it's 1, 2, 3, 4, 5, 6, 7. 7 plus or minus versions, 14. So there's 14 possible combinations. So remember in the previous video where we talked about the remainder theorem? There's an additional, if you think about it logically, the remainder theorem tells us that if f of x divided by x minus a, and the f of a gives the remainder, right? But if the remainder is 0, right, that means x minus a has to be a factor of f of x. That's what it tells us. So if we use that general concept, right, that means any values that we put 1 into this equation and it equals 0, then it's going to be a factor, so we could take that out. So it's going to be a 0. So what I usually do is that I leave the fraction to the end, and I'll usually start with the lowest numbers, starting with the positive. So it'll be positive 1, negative 2, positive 2, negative 2, positive 3, negative 3. So that's what I usually do. So I'll start with 1. So that's 2, that's 3, that's 7, that's negative 7, negative 6. So that's obviously got to be negative, so that's not going to work. Let's plug in negative 1. So that's negative 2, that's 1. So that makes negative 1. That's 7. So that's 6 minus 6, which is 0. So negative 1 is a factor. So factor equals negative 1. So what I usually do in this case is that let me erase all these because we already got like the factor. Usually I just keep the list there just so I know that we have the just so I remember the factors. Sorry, I need to erase everything for the room. So I know -1 is a factor, right? So I put in x plus 1 because -1 plus 1 equals 0. So I need to find out what I need to factor this out of the equation. So since this is a x and I need to get 2x cubed, I need to multiply by 2x squared, right? So that's my multiply this to get 2x cubed, right? So this multiply this to this, which is usually how I do it. That makes 2x squared. We have a 2x squared now, but we only need x squared, so I just need a minus the x squared, which make wait, sorry, minus the x, which is the linear term. So it's just 1 degree less. That's how I usually do it. So that's minus x squared. That's 2x squared. So that's x squared. And this one multiplied here is negative x here. So we need to get a -6, right? So we need a -6 more, which makes sense because then this will get negative x, this get -6x, which makes -7x, and this gets -6. So now we just need to factor this if it's possible. So what we will do is that what I usually do is that I'll split this up into 2x and then parentheses and then x. Because like the only way to multiply by 2 is 1 and 2. Usually I don't think it's fractions, but sometimes they could be. But usually in like a pre-calculus class is kind of simple. So the only way to get to -6 is like plus or minus 3 or plus or minus 2, or plus or minus 1 and plus or minus 6. So the only one that I think of that could get like somehow to a 1, I don't really care about the negative right now, is a 2 and a 3, because then the 2 times the 2 is a 4, and then the 3 kind of takes it out. So what I need to do is I put -2 and I put positive 3. So that will be -4, and that's 3, that makes -x, and that makes -6x, -6. So this is the factor form, x plus 1 times x, 2x plus 3 times x minus 2, which is equal to f of x. So you need to find the zeros here, so that's 0. That's usually, so by using the rational zeros theorem, you just find one of the zeros, factor it out of the equation, and then you do the rest of the uh the method. This is why I prefer using only the remainder theorem concept to solve this. So if you use the synthetic division and or long division, it's gonna take so long to like get this, and then you have to factor those out, which I really don't want to do. So what you do is that you get the use the remainder theorem. I use the rational zeros theorem to get the all possible rational zeros, and then you plug in those starting from the lowest and then to the fractions to get the value of 0. Once you get one value of 0, you kind of factor that out, and you start factoring them out until it's a quadratic, and you kind of just like get these clean numbers, and then you start solving it. So usually that's what I do. Get the 0, factor, solve. So that's x minus 1. That's -3/2, and then x, and this is 2. So these are the answers. These are all the zeros or roots or x-intercepts or what you call them. They aren't interchangeable. So that's the rational zeros theorem. Now let's move on to learning the bounds on 0. This theorem tells you like between what bounds like the zeros are. So it's gonna be something like this. It's gonna be like it's between x is -4 to like 4. So that's what it's gonna tell us. So using our equation again, 2x cubed plus x squared minus 7x minus 6. What we're gonna do is that we want the coefficient of the first term to be 1. So you're gonna factor out that 2. So that's x cubed. That's plus 1/2 x squared, right? Because 2 times 1/2 x is 1. And then that's minus 7/2. That minus 3. I mean, yeah, see? So that's 2, that makes 1, that makes 7, and that makes -6. So this is the same thing as this. So we're going to ignore the 2, and what we're going to do is that the first bound, you have to find the max. We have to find the max between 1 and the sum of the absolute values of these, or the coefficients, except the first term. So we're going to have the absolute value of 1/2, plus the absolute value of negative 7 over 2 plus the absolute value of negative 3. So that's our other bound. So the maximum of the first bound is either 1 or 1/2 plus 7 over 2 plus negative 3. So that's 8 over 2, that's 4, and that's 7. So the value of this, the maximum, is 7. So that's going to be our first bound. The next bound that we're going to think of would be adding 1 to the absolute value of the absolute value of the largest term. So the largest term would just be like ignore the negatives. What are you gonna? This is and we're not gonna count the first um coefficient in both the maxes for the bounds. We never count the first one. We just count everything else. So we're not so this one is 1/2. This is 7 over 2, and that's 3. 3 is just 6 over 2. So the maximum is um wait, plus the absolute value of the largest term. So the maximum of this is 3 over 2. I mean 6 over 2, right? So the maximum has to be 7 over 2. So plus the absolute value of negative 7 over 2 is just 7 over 2, but I'm trying to show the work. So that will get, so uh so we get 7 over 2, 2 over 2, that's 9 over 2. So that's our other bound. So our other bound is 4.5. So what it tells us that like the bound is between the lowest number. So the lowest number, this is our first bound, 7, or our second bound is 4.5. So the lowest of the two bounds is 4.5. So it tells us the bounds of 0 states that all the zeros, all the real zeros has to be between negative 4.5, because that's the negative version, and 4.5. So that's what it tells us. So that's the bounds on zeros. So for the first bound, it's just 1. It's just between, do you have to choose 1 or the sum of the absolute values of the coefficients other than the first coefficient, which is 7. So that's 7. So the other one, it would be the max of 1. The 1 plus the max of the absolute value of the largest one other than the first one. So that would be 7 over 2. You gotta ignore the negative because that's the absolute value of the term. So this would be 1/2, this would be 7 over 2, and that would be 3, which could be just 6 over 2. So the maximum is 7 over 2. So that's basically it for bounds on zeros. It's just inequalities for you to test points. So this is good in combination with rational zeros theorem because, like as I said before, like one of the possible factors for rationals is plus or minus 6 for this one, right? And the other one is plus or minus 1 because it could be. So the prob so there one of the probable factors is plus or minus 6, which is outside our bound because our bound is negative 4.5 to 4. So if this is negative 6 or 6, that's outside our bound. So there's you don't have to test this probability. That's what the bounds or zeros tell us. Usually I don't use this because since it doesn't give me the precise answers, I just won't. So I usually just use the rational theorem, zeros theorem and factoring to like do my work, as I said before in the examples. But bounds on zeros are like a pretty good uh process for you to like think about where the bounds are, so you don't have to test a bunch of points. So the intermediate value theorem, this one tells us that if there's a polynomial f of x and there's one point where x is equal to a and another point where x is equal to b, where a is not equal to b, and if f of a is negative and f of b is positive, then it tells us that that there is a zero, there is a root between x is equal to a to x is equal to b. Because you could just think about this logically. Like let's say how you have a point here that's a, right? and that's b, and one is negative, one is positive, it's sooner or later it has to cross the x-axis, right? So you have to just think about it. Like if it's continuous, it has to cross it sooner or later. It just has to have at least 1 0. So that's what it tells us. So let's use our example again, which is 2x squared plus x squared minus 7x minus 6. So let's say they give you f of 0, right? F of 0 is equal to 6. And they give you f of 3, which is equal to 36. I mean, this was equal to negative 6. Negative 6 and 36. Since this is negative and this is positive, that means there is a 0 between 0 to 3. Which is true because there's a 0 at x equals 2, as we said before, when we were using the rational zeros theorem to factor out. So this is true. So that's why it tells us. It's a pretty interesting theorem, but I usually just don't use it also. It's gonna be mentioned in precalculus class if you ever take it in school. But it's not something that you'll ever think about too much. It's like really kind of self-explanatory. Another this theorem kind of matters, but it's not really that much of a process of thinking. So if you have f of x and one of the roots are a plus bi, where a and b are like numbers, so let's just say it's like 2 plus I, then if the polynomials, all if its numbers are real, so let's say it's like x squared plus like 2x plus 5. 1 is real, 2 is real, and 5 is real. The only like they say this won't work if it's like I x squared plus like 2x plus 5, because there's an I here. Or if there's like I is not here and I is here. If there's an I anywhere, then it's not going to work. So for conjugate Peirce theorem, it tells us that if one of the roots is like a plus bi, then the other root is a minus bi. So if this is the if 2 plus I is a root, then another root is 2 minus I. You gotta remember which one is the negative. You don't want to put negative 2 plus I, which is not true. It's 2 minus I. Because if you think about it, it will be 2 plus I times 2 minus I, because you're like multiplying the roots. So it'll be 2 minus 2 plus I, because that's one of the roots, and then x plus 2 minus I. So what it does is that you multiply these together, and since if these add together, technically what it's going to do is that it cancels the I. So that's negative 2, and that's negative I, and that's plus I, and that's minus I. Oh, sorry. This one's not plus. This is a minus. So what it's going to do is that's negative 2, and that's plus I. So that's negative I and plus I. Those cancel out. So that's negative 2, and that's negative 2. So that makes negative 4. And these two multiply together. So that's negative, negative is a positive, so we just need to multiply. So that makes 4. That's minus 2i. That's plus 2i, because you see how that works. That's positive and that's negative. So those cancels out. And then the negative I square, and I is just equal to square root negative 1. So that would just be negative 1 times negative 1, which is just 1, which is 5. This portion is 5, not the equation. Okay. So you see how that works? You see how all these, this is 1, this is negative 4, and that's 5. They're all real numbers like this. You can't have like an I in there. So that's why the conjugate pair theorem works, but it's really simple. So you ever see like if a teacher like ever in a test or like some kind of instructor tells you that like 2 plus I is one of, sorry, my keyboard is dying. If they ever give you a 0 that is x plus I, and they say that like all the coefficients of the polynomial is real, then then another 0 has to be 2 minus I. Like it just has to be. Like there's no doubt about it. It's 100% certain that it's the x is the conjugate. And now we're gonna finally learn the last one, which is Descartes' rules of sign. So Descartes' rule of sign. This is another theorem where you're not gonna really be doing a lot of math. So like a bunch of these theorems you really don't need to do about math, but it helps you locate zeros or roots or x-intercept or how you call it. So basically, this one tells us like let's say we have an equation, right? F of x, and we have 2x squared plus x squared minus 7x minus 6. What you do is that you gotta look for alternating signs. And if there are like changes between the signs, like from positive to negative or negative to positive, then it's gonna be then there's gonna be a 0. So we have f of x first. So if we want to look for the positive zeros, this is only for positive zeros. So you have a 2 here, which is positive, and this is positive. So there is one sign change right here. So that's positive to negative. You can't do something like this. Okay, it's gonna have to be alternating. So it's gonna be from, if you put this in order, you have to look for the x squared to the x, and then x squared to the x negative x. So what it tells us is that since there's only one sign change from positive to negative here, it tells us that there is one positive root. So there's one positive root, and if we plug in negative x into x in the equation, we get 2x. Sorry, that's cubed. So, sorry, I need to erase this first. Equals to negative 2x cubed, because this is cubed. Okay. Sorry, I didn't write that right. And this would still be x squared. This would be plus 7x, and this one would be minus 6. Right? There is two sign changes right here. So from negative 2 to 1, so positive negative here, positive and positive, so there's no sign change. Positive to negative, which is another sign change. So there is two negatives, or there is 0. I'll explain why is it 0 right now. So these will actually to explain this one first. F of x, just leave it as the original equation. Looking for the sign changes between alternating will give you the positives. So looking for the if you plug in f of negative x into the equation, and the alternating sign changes from like here to here and here to here will give you the amount of negatives. And then you have to subtract by 2 every single time to find the like possibilities. So let me give a more clear example, because this one is only the x cubed term and it doesn't really help. Let's say something like 5x5 minus 4x to the 3 plus like 2x squared. Oh wait, sorry, I forgot a fourth term. Fourth plus like 3x squared minus 2x minus like 1 or something, right? So if this is f of x, then we gotta look for the sign changes. So there's one sign change from here to here, from positive 5 to negative 4. Another one from negative 4 to negative 3. I mean negative 4 to 3, and 3 to negative 2, and negative 2 to negative 1 is not a sign change. So there's three positives. If you subtract 2 from it, then there is going to be 1 positive. You can't subtract from 1 because that makes 0 positive. So what it tells us is there's either 3 or 1 positive root. See, that's what it tells us. So if we put like negative x in here, we get negative 5x. Sorry, negative 5x to the 5 minus 4x to the 4th plus 3x. I forgot the x cubed. It's fine either way. Cubed. Actually, let's just say squared. Actually, we're just gonna make this a cubed, and we're gonna make this a squared, and this will be a x. Okay, gotta do that. It's just easier to explain. So plus 3x cubed. Actually, no, that will be cubed. This be squared, and this be x. And this will get negative 3x cubed. This will be negative 2x squared, and this will be plus 1x. So if you substitute negative x into x now, right? So this will be the negative. There's only this is a 3. So there's only one sign change right here. So from -2 to +1. So that means there is only one negative root. Since you can't subtract 2 from it, then there is at least one negative root. That's what it tells you. There are at least one. So you probably want to look for that one negative. This is really good if you have it with the rational zeros theorem. I use this too, which is really helpful. So what I'll do is that I'll use the Descartes rule of sign first, and then I'll use the rational zeros theorem. Because like if there's at least if there's only one positive, or if there only one negative root, then I'm just gonna check for those for that one. So that if there's only one negative root, I'm just gonna check all the negative ones, starting from the lowest like integer to like the highest integer, and then to the fractions. So that's good. So if you're like using your calculator, it's also easier. But like usually when they do this, the teachers will be like, no, because like you know, if you have your calculator, can you just graph it? So that's the point. So I'm just going general and give you a more basic idea. So if you have like if your Descartes rule of sign say you have like 7 positive, like there's 7 sign changes just for the positive, then there's either 5, 7, 5, 3, or 1 possible zeros. You see how that pattern is going and subtracting by 2 every single time. So 7 minus 2 is 5, 5 minus 2 is 3, and 3 minus 2 is 1. So let's just say you have 7 positive sign changes. Then you have 6 to 4 to 2 to 0. So that's what it tells us. It's the same case for like negative. If there's like 7 negatives, then it's 5, 3, and 1. Or they're like 6 negatives, then 6, 4, 2, 1. You gotta subtract by 2, because if you because the Descartes rule of sign is trying to take into account imaginary roots, because this is only gonna give you the rational, the real ones, because the 7 will tell you like all the like there's 7 real roots, but they don't really know that. So if there's 2 imaginary roots, like let's say something like this, x plus I and x minus I, it's gonna say x squared plus minus I plus I cancels out, and you get a negative I squared, which is just -1. So -1 times -1 is +1. So you have this, and Descartes' rule of sign recognizes this as 2 roots. That's what it's telling us. But there is no 2 roots because they're both like imaginary. So what it does is that it subtracts like, since it has like 2 possible, right? What it kind of does is that it says that it's u minus 2 is 0, because it makes sense because they're 2 imaginary. So that's what it does. And that's why you do it for like every single one. So the possibility, so it's not saying that that there isn't like 6 negative roots. They're just saying that it's either 2, 0, 2, 4, or 6 negative roots. That's what it's telling us if you're using the if it's like 6 sign changes, which is usually not that many. There's usually like 2, 3, or 4, but I don't think it'll ever break the barrier for 5 a lot, because then you're gonna get a really big equation. So all these theorems, like all they do is just to help you find the roots of a polynomial. The ones that you really will want to use is just the rational zeros theorem. This one is really important. It helps you find the possible rational zeros. You want to use the conjugate pairs theorem. Like it's not any math, but it tells you that like it tells you that if 2 plus I is like a root, then 2 minus I has to also be a root. So you gotta know that one. Bounds on zeros, let me look at this again. Bounds on zeros and intermediate, actually, bounds on zeros you probably don't want to do because it takes too long and it only gives you like a bound. And what bounds on zeros do is just to limit the possibilities for the rational zeros theorem. But if you start like using the smaller method, the smaller numbers, it kind of becomes like irrelevant. It doesn't really matter. So you probably don't have to do bounds on zeros, but it's good to know for this video. Descartes' rule of sign, you should probably use it, but don't use it all the time. Like use it in like small increments, because like you don't really need to know all the time. Because if you just use the rational zeros theorem, like, and then factoring and then conjugate theorem, just in case like you ever have imaginaries, then you're basically gonna solve the entire equation. So that's the point. Intermediate value theorem, you probably don't need to think too much about it. Like like to refresh is basically if you have a negative point and then a positive point, then there has to be a zero between, which is kind of like self-explanatory. The precalculus just trying to make like theorems for you to like learn. And then the fundamental theorem of algebra, which is like the main point of precalculus, is telling you that if a polynomial has a degree 1 or higher, then there's at least one root, one complex root, so it could be imaginary. So, which is true, but you don't really, it doesn't really tell you anything, so I wouldn't think too much about it. So these three are the ones that you want to think about: the rational zeros theorem first, then the conjugate theorem, and the Descartes rule of sign. Descartes, I don't know how to pronounce it, so I'm sorry about that. I really don't. Uh, so thanks for watching, and I'll see you at the next math record video.